Fair enough. Okay. What I'd like to talk about today, unless there are any other questions about that, I'd like to talk about, in some sense, big data or achieving scale. Um, Again, I call this course data science, but you know, when data science emerged, probably 4 or 5 years ago, the big buzzword was big data. I don't, which I think is probably a buzzword that has kind of not aged as well as as some other things. But big data is kind of a world of where you've got data sets that are really massive, and that you're trying to deal with all of Twitter or all of Facebook or a substantial amount. Things where you've got genome sequences of thousands of people, where you deal with all the images in a big repository. Um, and working with data generally gets harder as the data sets get bigger for a couple of reasons. Some of them are just, I will say, technical, and some of them are more conceptual. Um, so far in here, we have specialized, we have talked mostly about dealing with what I consider to be a modest data set. One way that I think about it, if you can run it on your computer, it is not what I call big data. Okay, that I guess the distinction to me is, are you dealing with things that require more than one machine? Okay, that is really difficult to handle. And again, in many of the world's data sets are now, kind of incredibly large. Okay, when I last updated this slide, um, you know, if you're analyzing Twitter, if you're a normal, let's say a person who's not paying Twitter, you can get about 1 million tweet, about you can get 1% of the Twitter feed typically to play with. That's about 6 million tweets, and that will fit on your computer. But 600 million tweets a day is a big thing. Facebook, I heard, was dealing with 600 terabytes of data coming in each day. And that's something that doesn't fit on your computer. Google has, many billions of queries per day. Okay. So when you're talking about doing an analysis on data that is of this scale, it is qualitatively a different thing than the kinds of analyses that we're doing. I think that the scale of what we've been working on, if you can't work with small data effectively, you can't work with large data effectively. But large data has a different set of challenges. Any questions? So one of the ways that people kind of talk about big data when they were, is they describe it in terms of V's. Okay, and one of the obvious one, what makes data big, is whether, what its volume is. You can kind of view a dimension, a data set as being a function of what dimension is its parameter. Okay, whether it's measured in megabytes or terabytes or God knows what. Another issue is what velocity. How often does the data change? So when you're dealing with video data, let's say if you're monitoring a constant, video feeds that are live, they are always, have to monitor it in real time. A lot of the analyses, certainly the analyses we've done in this class, have all been on batch data sets that don't change. Okay, but many data sets of interest change. There's new data every day, and you got to deal with it. Another issue is what we would call variety, that many of the data sets that, let's say, people talk about, like, let's say if you're Facebook, the data you deal with if you're Facebook is kind of a mix of text, and people upload videos and pictures, and they also link to other friends, so there's network data involved. So there is difference between whether you were given a table like a a spreadsheet file, okay, or a traditional database, or if you're given one of these multimodal things. And typically big data sets involve multimodal analysis. And sometimes people add a fourth V, which is veracity. How much do you trust? As data sets get larger, there often are confounding artifacts and bad things in it, okay, that makes you have to worry about its veracity. Any questions here? So just to sort of picture a little bit about data sets. Again, at one point we were talking, early on in the semester, I had you look at all these videos, and these were kind of the data science challenges we had here. And my question is, are any of these, could they possibly have benefited from big data, really big data, okay, if you could have gotten your hands on it, okay? Do any of these problems look like they would have led to worlds where there really existed large data sets for them?
Maybe the baby weight and the future gold oil price is really the
two. You're saying baby weights. If I had a record of every baby that was born in the world, if I had complete access to medical records of everything, maybe we could think about that. Okay, so you could imagine a world where certainly the data sets that if you want, if you could analyze a hospital's medical data on people, that would qualify as a big data set, and maybe that would be interesting. You said gold and oil price. There becomes a question of, I guess, at what granularity you're looking at something. If you're looking at the prices of a commodity every day, okay, well, there have only been, a few 100,000 days probably where they have traded gold where they have records of it. That wouldn't be very large. But certainly some of the financial data sets where they're measuring, you keep track of every single transaction, every time, every stock that was sold, every time there was an oil price future that sold. Something like that probably does approach a data set that is interesting. So that's why hedge funds probably use big data set. Have a lot of computing involved. I might say that the weather data, the data set that certainly the National Weather Service has weather data, satellite images and things like this that are probably large enough that they are measurable. But most of these other problems, and even the problems we talk about, note that they could be addressed with much more modest data sets than we're talking about here. Any questions or comments? Okay. One thing that I once heard described that actually did resonate with me, that when you hear someone talk about big data, you should be realizing that they are talking about bad data, okay? Usually when massive data sets kind of get constructed, not because someone sat down and designed what would be a great data set for solving your particular problem. They are kind of the results of kind of an opportunity. If you are Mark Zuckerberg, you suddenly find that people are using your service, you might as well log everything, okay? Or you suddenly, change features, and if you're Google, you suddenly realize, okay, I might as well save every query. Okay, I can afford to do it, and it's probably interesting, and I do get lots of these things. There's kind of a difference between a curated data set, where I think somebody is trying to construct data for solving a specific problem, and data sets where you kind of are just assembling it as the result of some natural process. These data sets that are assembled of by natural processes are often, of course, incredibly useful. That's why you save them. But recognize that they kind of come with certain problems. If you are looking at a data set of the internet or dealing with Google or things like that, one thing you have to deal with is, spam and machine generated content. One thing that, natural language translation programs, that you've used these programs that translate from English to any other language or vice versa. And the way that they were built was by looking on the web for training data, for text that existed in two different languages. And this was a great thing to some point. But then once you started getting Google Translate on the web, suddenly most of the translations to be found were the result of these automatic translators and no longer people. And so the machines couldn't really learn from it anymore. Okay, if you're going to try to learn from you've got to get rid of machine generated content. That's one problem. Another problem is that when you try to look at data that you find, you get unrepresentative participation. We had at the early ages of the, let's say social media, we had a company called General Sentiment, which was trying to look at Twitter feeds and other social media feeds and try to get sense of how people liked products and things like that. Well, recognize that anything we heard from were people that were using Twitter, and this was a subsection of the universe. And things that we learned from, Twitter users may or may not reflect back to people who don't have computers and don't do that much. So that's one issue that comes up. There's problems with, what I'll say, temporal changes. Typically what happens is if you have a logging system, you will keep logging everything that has happened. And so you have data from a long period. But sometimes things happen, where the system that's doing the logging changes. And so what the meaning of the data in the log kind of changes. I believe I mentioned and discussed about Google flu trends at one point. This was this model that was going to try to predict how sick the population was by how often people typed in the word cough and sneeze into Google search engine. But apparently, that system got thrown off because at one point Google started recommending, if you click this, how about this? And people started entering a lot more related queries than they had used to do before. So the search log data looks the same, but kind of what it was meaned and how it was generated changed over time. And this is the kind of thing that you often lose when you look at a data set. The other thing, I guess, that happens with a big enough data set is that typically there are power law phenomena. And power law phenomena means that there are a small number of things that dominate, okay, that are asked about over and over and over again, okay? And thus, in some sense, if you have a big ambient data set, a lot of it is repetitions of the same query, the same phenomena, okay? That doesn't mean that these big data sets are bad, but these are issues you have to deal with. Any questions? Now, the machine learning algorithms that we've talked about in here don't always generalize well to big data sets. Okay, so I have talked here, I like linear regression, I like logistic regression. Okay. Linear and logistic regression, typically you have a certain number of variables that you care about, which I'll say is measured in hundreds or something like that, the number of dimensions. You're trying to build a model to fit every example. If you have millions or billions of rows, each of which only has 100 dimensions, you can't really build an interesting linear model that will benefit from 1,000,000 examples, okay? If you need 1,000,000 examples to fit the thing right, and you only have 100 dimensions worth of features, well, then your model can't possibly be very good, okay? Your model's only going to be good if it can generalize from the things that it has. So so if you have a large number of examples, you can't, it doesn't really benefit a model which has few parameters. Deep learning is, of course, a different thing. Deep learning is a world where you have large numbers of parameters, okay? And that's one of the reasons why deep learning is a good thing, okay? Is that it has enough parameters that it can benefit from a massive training set and require a massive training set. Some of the other models that we talked about that might have large parameters, like nearest neighbor models. If you have to search through 1,000,000,000 examples to find the nearest neighbor, well, the running time of your thing becomes so bad. Okay, so many of the algorithms we talked about don't generalize very, very well to huge data sets. Okay, one thing that's clear is that if you have a huge data set, your algorithmic complexity had better be near linear. Okay, so if you have an n squared algorithm and n is 1,000,000,000, you're in trouble. Okay, if you have an n or an n log algorithm, you're probably okay. Okay, any questions about that? Okay, and again, if you're building a matrix, any matrix had better be kind of sparse, because if you have a 1,000,000,000 by 1,000,000,000 matrix, you can't represent that in a machine or anything like that. Any questions or comments? Now, in general, what I think that most of the big data stuff that has proven to be useful is that you can kind of, if you can't use linear, effectively use, billions of rows of data to train one model, one thing that's proven more effective generally is to use your billions of rows of data to train millions of models. So where, let's say, this stuff has come in very handy, has typically been on customization. If you have a large amount of data, if you have a modest amount of data on a huge number of people, it's perfectly good to train an individual model for everybody, okay? And maybe share some data from other, across individuals or similar people. But one thing that, let's say, the large data sets do is enable you to build lots of individual models, okay? And this is more in the spirit of the kind of stuff we've talked about in this class, okay? And is customization and things like that. Any questions?
Why do we call that customization?
Why do I call that custom? Well, again, that kind of in the olden days, Google did the same thing for everybody. Okay. I'm occasionally very, very proud when I look on Google and I see how often something by me or mentioning me appears in my searches. Or and the reason, of course, is that Google, it's not that I'm that important and not that too many other people see Skeena, but the fact that I have asked for things and it has built a model around interests for me, okay, means that kind of what I see is different than what everybody else sees. Okay, at the beginning, again, I am old enough to have been alive at the beginning of Google and search engines. In the beginning, everybody saw the same thing. And now your experience is quite customized. And the reason it's customized is basically that they are building an individual model for every single user. Does that answer your question or not really?
Yeah, I think it does. So when you're talking about customized, you're saying that you aren't just learning one model for the data set, you're learning multiple so that in specific cases you can get better accuracy.
Yeah, so right. So you would like to improve the accuracy of the search engine. The accuracy depends upon, you want the documents people are going to click on the most. That's not necessarily, it depends somewhat upon what your interests are. Okay. If you're typing in Jaguar, okay, whether you're interested in animals or whether you're interested in cars, okay, is something that's probably true in your profile. Okay. So the performance of these systems are improving, okay, because of customization. And the reason you can do customization is because they have modest data on enough data about you to do some kind of customization. Okay, and I think that is more a world of training millions of models rather than viewing it as one big model that is being trained. Any other questions or comments? So building individual models is one thing that you can do if you have a lot of data. Another thing that I think is very good and useful to do with when you have a lot of data is to throw much of it out. Okay. One thing that you can do is you can be a lot pickier in your cleaning. When you do your data cleaning, if you have a small number of examples, you have to squeeze the most that you can from each one. When when you're in a data rich environment, usually you want to work harder to delete the stuff that isn't so relevant to you. Okay, and that's an important part of what you're dealing with. Again, when we had general sentiment, one of the things we were doing was analyzing the Twitter feed. You know, we were trying to do analysis on all the feed, but eventually we figured out that our NLP was only really working, designed to work best on English. And so if you instead started and took a look at, you wanted to get a sense of how much people were talking about Toyota, okay, or whatever company was a client of ours, okay, you would want to throw away, okay, all the non-English, throw away all the non-English tweets, okay, throw away all the bots, throw away all the things that don't look like they're being written by people, okay, and you will still, you will have much cleaner data, and it will leave enough for you to do some analysis here. So doing this kind of filtering involves some kind of application specific knowledge. You have to kind of know what you want to do with the data, and think about what you want to make go away. But when I have a big enough data set, I want to be picky about what is worth including and what isn't worth including. Any questions about that? So even if the data, you have a lot of good data, okay, even if all the data is good and it's stuff that in principle you want, often you're still in a problem where you want to take a small subset of it, okay, and that working with a subset of the data can be much better, okay, can be, it can have advantages over trying to work with the whole thing. Again, if you have a simple model, okay, fitting a regression model with 100 dimensions, you will do just fine with 1,000 examples or 10,000 examples. Having millions of examples isn't going to lead to a better model, okay? So, but you want your examples to be representative. Typically, you're better off under these cases taking a subset of the data, okay, and training your model on that, okay? When you have an appropriate sample, it's easier to visualize. When we were doing visualization, we saw in a world where many people were able to draw these dot plots with these huge dots that completely covered everything up. Okay, I said make the dots smaller. If you have so much data that even when the dots are small, you can't see them because they overcome everything, it's often a good idea to take if you took a representative sample of the data and did a dot plot from that, that would be enough to give you a visualization that you can kind of deal with. And we also talked about subsampling when we were talking about, building test training and evaluation sets from data. Okay, so there's often reasons why we want to take our data and partition it into subsets. Any questions? Now, that said, there's good and bad ways to extract samples from a given data set. One way to do it, if I need n records and I have a big file, one way to do it is to just take the first n records from my file and call that my sample. What is an advantage of doing that? Okay, one is that it's simple. One is it's reproducible. Okay, if I wanted to later go and find out what were the first 100 records from the file, I already would have that. Okay, but if you subsample by just taking the first n records, okay, it often creates biases in what the meaning of that sample is. Okay, because the order of a file, okay, typically reflects something about it. Now, again, if you took the file and you randomly permuted all the rows and took the first n, now maybe you've got a unbiased sample of the records from the full file. But there are often interesting biases that kind of come up that you won't see if you just take the beginning part of a file. Obviously, if you have a log, okay, if you have data is on a log, typically the oldest things were written first and the newest things are at the bottom, okay, or perhaps vice versa. So it should be clear that if it's a log that's being accumulated over time, sampling the first part is going to be a temporal bias. There's other interesting biases. If you had the names, if you had a phone book, okay, if you take just the first record, you're going to get everybody whose last name begins with A. And there are often biases on here. My understanding is you have a lot of Arabic names begin with A, have last names, letters that begin with A, al somebody, okay? And other ethnic groups may not use that as much. So you end up creating biases if you do that. Even things that, when you sort them, look like they are going to create an unbiased thing, will end up creating biases. So each of you has been assigned a social security number, or almost all of you, I trust. If you ever work in the United States, you've been assigned a social security number. If you took your records and sorted everybody by social security number, and you took the first n records, what bias would you create there? Does anybody know? If you sort people by their social security number, what do smaller social security numbers mean?
That you got yours earlier.
Does it mean that you got yours earlier? So it's if they counted social security numbers, if the first person to get one had their number 00001, then you're that. But the answer is no. It does not record an age bias. Does anybody know what the social security number would call if you sorted everybody by social security number?
Are social security numbers given out at the hospitals that you were born at?
They're given out at the hospital that you're born at. Actually, the answer is no. Okay, to be honest with you, they're not given at the hospital you're born at. Typically, people apply. Actually, that's a good question. Let me be careful about this. It may be. I don't know if the rules of. First of all, some people were not born in the United States in hospitals. So certainly these people are applying for Social Security numbers. But the answer is the hospital. It may be that many people get their Social Security numbers at birth, but what the hospital doesn't actually give it. What is true is that Social Security numbers, the first three digits of a Social Security number, tells you something about the state where you got it from. So the Social Security numbers were kind of carved into regions, I think, where the first 5 digits are a blend of, were allocated in kind of blocks based on what state you were in and what year you applied for your card. Okay? So all of you guys, if we sort you here, there's a lot more of you will have New York license plate, will have New York Social Security numbers. Okay? Either because you were born here or more likely because you were processed as a resident of New York. And this produces, so there are biases. If we picked who had Social Security numbers most like Skeena, you would get people who were from New Jersey from about my time. Okay? Any questions about that? So often there are biases in how these things are worked. There was once this Kaggle competition where the person who had constructed it had built a file of positive examples and a file of negative examples. And they basically concatenated them for the test and training sets. But they included the line number in the file as one of the columns. And the result was kind of the line number of the file, basically told whether it was positive or negative, just as an artifact of how it was built. So bottom line is, truncation is a bad idea. What is a better idea? Okay. Random sampling may seem like a better idea. What is random sampling? You have a record, a file with n records. You randomly pick, if you want to end up, one possibility is you say, I want to see roughly 1% of the records. So one possibility is for every record you flip a coin, and if the value, the number is less than 1/100th of the range of the random numbers are drawn from, you take the record. Okay. This has no explicit biases, but there are problems with this kind of random sampling. One is that some regions are just bound to be oversampled. Okay. If we have a class, a file with exactly half men and exactly half women, if I take a random sample of this, am I going to have half men and half women? The answer is, in expectation, maybe kind of. But in actuality, there will be a difference between the number of men and women in my file. It's like, there's a standard deviation, and such a thing would probably be something like on the order of square root n. Okay, so they would probably be, you'd have about n plus or minus square root n, n over 2 men, n over 2 plus or minus square root n men, and n over 2 plus or minus square root n women. Okay, you're not going to get the exact same frequencies. Another problem with the random sampling is that these are not reproducible unless you have the same random number generator and seed. So if you want to repeat the experiment, you sometimes can't do it. Okay. And if I try to run many random samples, I want to do this multiple times. If I said, give me a random sample for test, a random sample for training, there's no reason why those random samples are going to be disjoint. And I could very well have records that are in both my evaluation set and my training set. Any questions about that? Okay. Now, a better way to do this, if let's say you need a random sample in, for statistical reasons, okay, the method that is used in polling and other methods is what they call stratified random sampling. If let's say I want to sample people, I may want to say I want half the people to be men and I want half the people to be women. Okay. If you're trying to, let's say, do a poll, let's think about, let's say, like you're a company that wanted to do a poll of the, for the who was going to be elected president. If you just call people at random, maybe men are more likely to answer the phone than women, or vice versa. Maybe young people don't have phones that can be reached. Okay. Typically, what these groups will do is they will break up the population into buckets. Okay, maybe they will sample them by age buckets: young, middle, old, young, middle, old. And they will know what fraction of the population falls into each bucket. And then when they do their random sampling, they are going to keep sampling people and they will find what bucket you fall into. And they will make sure that they fill their quota of how many people they need from each group. Okay. So the good thing about this means is that after you've done your random sampling, the demographics of your group are going to match the demographics of your sample will match exactly the demographics of your group, of the underlying population. Any questions about that?
Doesn't that introduce a lot of human bias to your data?
Well, does it take human bias? You could say human bias, or it could say human knowledge. If you know that men and women are different things and that they tend to have different behavior in voting, then making sure you have a representative number of each group is not a bias. It's it's exploiting a knowledge. Note that if you just sampled them by randomly, you're going to get there is almost certainly going to be a sampling error in that you're going to get either more men than you should or fewer men than you should by chance. You know that, like I said, it's a proportional, presumably, to about the square root n, if n is the number of things that you're sampling. So if, let's say, let's think in the last election, as I recall, as I understand, men voted for Trump, women more aggressively voted for Biden. That is why Biden ended up getting more votes. Okay? If there is a strong difference in the behavior of the two groups, if your poll is going to let the mix of the two populations happen by chance, there is going to be a lot of random fluctuation in the outcomes of one poll to another poll. This is why the stratification is a good idea. Any questions about that? Another way that people could do it is that you know what percentage of the population are young men. You sample randomly and you identify who is a young man. And then these people will get their, let's say, vote, their opinion will be weighted according to the underlying population. This has the property that it will, you're going to make it. There's going to be a properly weighted population. The outcomes will be properly weighted by the distribution in the full population. The bad thing is, if you accidentally undersample and you only get one young man, that person's opinion is going to stand in for this entire block of people. So again, you could sample randomly and then try to adjust it to the underlying distribution. That has the property that it's easier to do the poll. The big problem is that where there are populations that are undersampled, the background is going to, a small number of people will represent a disproportionately large members of their class. Any questions? The bucketing here, again, is something you have to do based on knowledge. In the 2016 election, one of the reasons, the pollsters were very surprised by the fact that how well Trump did. They thought that in that case Hillary Clinton was going to was polling much better than she actually performed in the electorate. And the reason the pollsters figured out, or thought they figured out, was that when they were sampling men, they had broken down their groups by what population. They'd broken them down by gender. They'd broken them down by region. They'd broken them down by age buckets. But they didn't break it down by education. That if you were a man of a particular age, okay, your propensity to vote for Trump depended upon maybe whether you had gone to college or not, okay? And so one of the things that they did in this year's polls, in order to make the polls to produce better results, they thought, was they did another stratification based on education. Now, the polls ended up missing by about as much as they did the previous time and in the same direction. So it's not clear they really fixed their problem. But that was one of the ideas that they used to try to fix it. Any questions?
The more strata you have, like exponentially less per group you'll be able to get, right?
So the more strata you have, the harder it is to find enough people to fill each group. That is definitely true. Okay, and so there is an engineering question of where do you set up your strata so that it matters. Okay, maybe if you insist on breaking up age groups by every single year, you have a lot more buckets you've got to fill exactly, right? If you say, oh well, all college students, all people from 21 to 34 are identical, then you're kind of lumping that strata in, as opposed to polling 8 people from each year separately. This is fine so long as the group behaves in a reasonably coherent way. And this is, again, engineering about the population. Any questions? But yes, if you are from there's certain strata that that may be very, very hard to poll, okay, that are important to reach by this thing. And that a lot of the work that makes it hard for a pollster is to fill the strata intelligently. Historically, pollsters, for legal reasons, have to call landline phones. So I have a phone that plugs into the wall. My guess is many of you do not live in homes where the only phone you have is your mobile device. Because of a quirk of the law, pollsters aren't supposed to call mobile devices, okay? And thus, if they're going to have a pollster who's going to try to fill up their strata by calling people, it may be hard for them to find an under 18-year-old, boy who lives, who owns a landline. Okay. Any questions about that? But stratified random sampling is an important thing if you're going to get polls that mean something. Any other questions about polling or anything like that? Now, one way that is, in some ways almost as good or maybe even better in certain ways than random sampling is what I will call uniform sampling. Suppose, let's say you want to end up with M records, okay, or take it back. You want to end up with, if you have N records to begin with, suppose you want to get a sample of size N over M. One possibility is to just take the file and take every record that is congruent to I mod M. So maybe, let's say you take every 10th record starting from the third one. That would mean you get the third record, the 13th record, the 23rd record, the 33rd record. If you do this, this satisfies several of the problems that come up with random sampling. One is I know that I'm going to end up with exactly how many records I'm going to get at the end. I am going to know that, this is reproducible. If I do this on a sample and you have the file and I have the file, if you want to run something on my sample, all I have to do is tell you what my I is and my M is. Okay? I can get disjoint samples by simply changing I. If I now want a disjoint sample of the same size, let me give everything that's congruent to 2 mod 10. Now I give you the second record, the 12th record, the 22nd record. Okay? This is how Twitter actually, in some sense, is able to give you a stream of every 1% of its feed. They basically have a number associated with every tweet, and they give you everything that's congruent to 1 mod 100. Okay? Any questions about that? So even if the file is sorted in some way, this kind of breaks the problem, breaks the biases associated with sorting the file. So if it was sorted alphabetically, you're going to still get the same number of A's as Z's, if they were the same number of A's and Z's in the original file. Any questions about that?
Yes. So as an alternative to this, why not just randomize the file with a seeded number and then just take the first N?
So one possibility you're saying is to randomize the file, but recognize that that's a big deal. Does Twitter want to build a file of all of its tweets and randomize that? That's gonna rattle the disks around a great deal. So that is not as good a solution as this one is. Okay? Any questions?
This does seem to introduce a bias, though, which is that if you have like maybe every fifth tweet, then you ensure that you'll have no consecutive tweets. Does it matter?
Okay, so the question is, are there still biases here? The answer is probably yes. And they are, let's say you would not get, 2 tweet, So for example, anyway, the answer is there probably are still potentials for subtle biases. Okay, do I believe that? I believe that. Okay. Pragmatically, these biases have to be more subtle than what we had been seeing before. Okay. So the answer is there's still there's still a chance for some subtle biases. I will give you that. Okay. But as a pragmatic thing, this is often a good idea. Any questions? Now, one other problem that comes up is, what if you want a uniform sample, a random sample of things where you have a stream, where you don't know how many things are coming? So there's a typical problem might be, let's say that you want to get a random stream of tweets, let's say on a particular subject. Let's say I want to get a random subset of Trump tweets, of tweets that mention Trump, okay, over the course of a day. Now, maybe people talk about Trump in the middle of the day. Maybe they don't. Maybe they'll get tired and not talk about him at the end of the day. You don't know. Suppose you want to get a sample of 100 tweets, okay, from a stream, okay, without storing the whole stream. How can you get a random sample of this? Do people kind of see what the problem is? Let's forget the Trump thing out of it. You have a world where I want to get a random sample of the tweets in a given day. And I want to get a sample of, let's say, 100 tweets over a given day. And I'm only allowed to store 100 tweets, okay, instead of storing all of them. If I stored all of them, I could randomly sample them at the end. But how can I sample them in a way such that they are all uniform, of uniform probability? This is actually an interesting algorithmic problem, and tends to be something that they ask on interview questions at companies sometimes. Does anybody know how to do it? You have a fixed memory of size K, okay? You'd like to end up a sample of K tweets from a big thing of size N, but you don't know what N is in advance, okay? How can you do that kind of random sample? One way to do it in an unbiased way is to start out for the first K tweets or elements, we fill our array of size K with the first K things. Certainly, if there's only going to be K, N is going to be equal to K. We're only going to get a total of K items. A random sample of size K, the only random sample of size K would be the whole set. So if we fill up our thing with the first K, I'm going to call them tweets in here, but let's call them items, the first K items. Then I have an unbiased sample at that point. Now what I am going to do is, for every successive item, okay, if I am dealing with the nth item, okay, what is the probability it should be in my random sample? The nth item, okay, if there are, I'm going to end up picking K of the items out of the N. The probability that the nth item is going to be in my random sample should be K over N. So I flip a coin, and if I give myself a random number. If that random number is less than K over N, I should include the nth element in my random sample. If not, I should discard it. And if I include it, I can take my current sample and pick any of the elements at random and discard it. So the way to do the stream sampling in an unbiased way is, for the nth record, flip a coin to decide whether it should be one of the K elements in that I pick, meaning that my random number, if I pick a random integer from 1 to yes.
Oh, I didn't realize my mic was on.
Okay.
I did have a question though. Is this algorithm susceptible to numerical instability?
Is it subject to numerical instability? So what is true, I guess what you're saying is that I'm going to have to pick a random number. Okay, I'm going to have to pick, if you think of a random real, okay, and tell whether it's less than or equal to k over n. As n gets bigger and bigger, okay, accurately sampling a random number so that it's, it's probably, so that it's meaningful of whether or not it's greater than, or it's smaller than k over n, eventually becomes hard. If I've got a 64-bit number, 1 over 2 to the 64th is the kind of smallest probability that kind of I could hope to capture here. So you're right that as n gets large enough, I have to take pains in generating my random numbers so that that I will be able to pick one and meaningfully tell whether it is in the, it is less than or equal to k over n. Okay, but I will claim that if you allocate enough bits to this thing, you should be able to do an okay job. But if we agree that for large n, this would be a problem, and small k, this would be a problem.
Professor, I have another question,
Yeah.
or a different question.
What?
Isn't this method kind of just subtly biased towards newer, I guess, tweets in this example?
Is it subtly biased towards it? The answer is no. Again, if we stop after, if k was equal to n, then wait, are you saying is this subtly biased towards the newer ones or the older ones? Which ones do you think are biased?
I feel like if the stream continues for a very long period of time, you're more likely to have tweets from the later part of the sampling than the earlier part.
Let's be clear. Let's just argue again. You have to kind of argue with this inductively. Okay, I guess the proof of correctness is kind of an inductive proof. The basis case is when you have k is equal to n, and then it's clear you've got the only possible sample. So originally it starts out as a random sample, and each element is equally likely to is being represented with the right probabilities. It should be clear that the last sample, okay, is being picked with the right probability. That if you have a random sample of size k out of n items, then in fact the nth item should appear in k over n of those things. Of those things. So certainly the probability of the last item is correct. And it's going to replace an element randomly selected from 1 to k. The second thing is we're going to randomly select the position of who the last element's going to replace. It's equally likely to replace the old one or the new one. Okay? So bottom line, this is correct. This is statistically correct if you do this.
My confusion, I guess, is that for every time you're going to replace something, you just have more of a chance, not more of a chance, but rather the older tweet is going to be up for elimination more often than the newer tweet.
Is always in here. Again, it's kind of like a process. You want to know, are you going to be on top at the end? Are you going to be one of the, let's say we were only going to pick a sample of 1, okay, for vision. Item number 1 is sitting in the sample at first. The only way it survives is if nobody gets lucky enough to replace it. Okay? So item number 1 is going to be sweating through the entire, so the good thing is it's in the club, okay, at the beginning. It's just a question of, is it lucky enough that nobody else comes by and takes over, knocks it out? The last guy has a 1 in n chance of joining the club. Okay? And this is about the same thing. Okay? So basically, as the comment says, basically the survival probabilities per, work out. So basically, none of the other, again, if we think about it, what's the probability? Let's think about this item. What's the probability it survives? There was a 1/2 probability it survived the first time. Okay, after the second, which is what you would want after if we tried the second item. If there were n was 2, there was a 1/2 probability that one would survive. For 3, there was a 1/3 chance it would succeed. That would mean that there was a 2/3 chance, okay, it survived. Now it has a 1/3 chance to survive. Okay. The next one has a 3/4 chance of surviving the next round. Bottom line is, at the end of this, there's going to be a 1 in n chance that the first item survives all the way to the end. There was a 1 in n chance that the last item was going to be the one to replace it. Everything works out fine. Any questions about that?
I think I kind of get it now. Is K just... But how can you continue to do this once you hit your cap for K?
No, you're going to, once you have filled out...
once you... I see. Okay.
You're going to basically flip a coin with probability K over N. Does the item survive? Okay. If it survives, then it's going to eliminate somebody who was already there. Out of the guys that were already there, it's equally likely, any of them are equally likely to be there. Any questions? Okay, good. Any other questions about random sampling or anything like that? Okay. Okay, so again, what can I do with big data? I like the idea of throwing as much of it away as I can, so I have small data. But that said, sometimes you do have a large data set, and you do want to actually work on the entire data set. And in order to do this, like I say, I think that big data happens kind of when you start having something that requires more than one computer to do it. And when we talk about using multiple computers, there is a distinction between what I will call distributed computing and parallel computing. I think of parallel computing as something that happens on one machine. Okay. So, sometimes, in the olden days, you had sometimes, supercomputers of that had many, many processors on it. You right now live in a world where every CPU that you get has multiple cores. Okay. Parallel processing is the kind of thing you do on one machine. You use threads, you use operating system processes. This is, I would say, one machine, okay, multiple processors. Distributed processing is a world where you have many different machines, many different computers, okay, which are using network communication. And when you do this kind of parallel processing, our dream is that we have jobs that don't require much communication between things. Ideally, if I wanted to divide a job among a bunch of processors, if I could divide it among them, they each work independently and don't have to talk to each other. That is the better thing. When solving the problem requires communication, that is when things get more difficult. Okay, any questions?
Quick question about the terminology. I took a course called Parallel Computing, and
Yes.
in that course, it was about supercomputers that were networked together, and we call that parallel processing in the course.
Okay, so in the world, first of all, names are what people use them for. I will still distinguish that there is it's interesting, in the, and again, in my era, if you said what was a supercomputer, you live through things, okay? There was a time when Cray, when I was a student, Cray had these supercomputers, which were things that, they were these amazing machines that were individual units. They looked like strange things. Like the Cray one looked like a piece of furniture, okay, because they had to be wired in a way so that everything was as close as possible. And they had another one that looked like a fish tank because it had to sit in liquid coolant in order to not get overheat. On these worlds, there was a clear distinction between things that were on one machine and things that were on a network. Now, those kind of machines have gone away, okay? And so you're right that the people who do high performance computing live in a world where they are dealing with multiple racks of machines wired together. But even here, there's a difference between the quality of the network and the network performance of what you would get when you are dealing with a high performance machine that was designed to work together versus a much more loosely coupled set of machines. Okay, when you're buying machines on Amazon, God knows where they are. They can be all over this data center. They can be all over multiple data centers. Okay, that is a world of distributed processing. Bottom line, there is a separate world of programming multiple cores on your machines rather than programming things where there is a lot of network communication. Okay, and that there are different techniques and different ways of programming and different techniques that end up applying with them. I agree with you that high performance supercomputers today are networks of other machines. Okay, but there is usually a lot of art that goes into the designing of the network so that they behave in a sensible way. Any questions about that?
So distributed processing would be if I just buy a bunch of old Windows 95 PCs for $5 a piece and wire them up in an Ethernet cable.
That would be more akin to what I'm thinking about. Let's say yes. Okay, typically the way you would do it these days is not by buying your old PCs. You would go to Amazon and you would rent a bunch of machines in a cloud. Okay, or even if you have a rack, actually, even if you buy a rack of machines, you'll connect them together. Typically, I'll say that you program them in different ways. Okay, and I will say in distributed machines, you're worried about the quality of the network. That's probably, I guess, where I will say the differences. Okay, any questions? So the easiest way to do parallelism or distributed computation typically is based on when you're in a big data world. Okay, is when you are doing partitioning. Okay, so what's the easiest way to exploit either many processors or many machines? Okay, one is to partition the data into different pieces, spread it around among different processors and or different different machines, and train completely independent models. Okay, so several times in this class we have talked about worlds where you were training basically independent models. We thought about multi-class classification, when you were doing all versus one versus all versus the rest classification. If you had K categories, you were building K different models. This is a perfectly good thing to do in a parallel way. These models are being trained independently. Okay, so that's a good thing. The hard part is that if you're training independent models, or if you're training models on different machines, it often becomes hard to combine the models together, the results of the runs together. Okay, and this is where there gets to be a more of a challenge in dealing with multiple machines. One way that people exploit, again, parallelism or distributed computation is, again, I like independent runs where they don't have to communicate. One thing that another place where people build independent models is on something called grid search. Often in any kind of a machine learning world, you have a set of data you want to train and build a model of. There are certain parameters in there that are kind of, we would call them meta parameters. Okay. One possibility is to, like for example, in k-means, when you did a k-means and clustering, you needed this not only to have the points, but you also needed to specify what k was. Okay. If you wanted to find what was the best k for k-means clustering, this is a grid search. Okay. This is, if you're doing a linear regression model and you want to employ regularization, there is a certain parameter that you will use. How much do you want to favor fitting well versus removing parameters? Okay. These kind of things represent independent, independent models. This is a good way to use parallelism. Okay. Because again, we can run them in parallel and just take the one that is left at the end. Now, when it comes to distributed computation, one thing is that the thing that makes distributed computation hard is that that the complexity of things that can happen changes as a function of n. If you have one machine, your goal is to keep all of your cores busy. This is something you can do by writing threads. It's something you can do by setting up processes. There's not a lot of infrastructure you need there. If instead of having one machine, you've got two, machines, or three, or something like this, you still can kind of juggle the processors and carve up the load between the machines by manually, and that's not so bad. When you have a world where you have a very large number of machines, 50, 100, 1,000, you need to employ some kind of a system for managing the multiple machines. Okay, that's where the MapReduce paradigm for distributed computation turns out to be very important. Any questions? Again, I want to emphasize that things change with scale, okay, and that there is greater complexity as n gets larger. And again, right now everybody is a pandemic. No, there's no such thing as a social gathering. But you may remember back to the not so distant future where people had conferences, let's say. When you have, as n gets larger and you're trying to arrange a social gathering, there are things that change as n gets larger. Okay, if you want to figure out what you're going to do, okay, by yourself, this is no problem. When you have a couple of people, okay, you got to coordinate among yourselves. Everybody can talk to each other and weighs in. By the time you get to like 10 people in a group, if the group is going to do something, somebody is going to take charge of that. Okay? Maybe you can have 10 people go to a restaurant, but one guy is going to say, we're picking this restaurant at this time. Okay? When you're having a wedding in the United States, maybe a large wedding in the United States might have 100 people in it. One thing that's true is that even if a wedding takes place in a restaurant, the dinner takes place in a restaurant, people are not allowed to order what they want. There's a fixed menu. Why is it? It's because it's too complicated for a restaurant to suddenly deal with 100 different dishes, okay? And to be prepared to deal with that. So you require fixed menus. Okay, when you go to a wedding of 1,000 people, I have been to 2 weddings in India. They had like 6,000, close to 1,000 people at them. If so, nobody knows most of the people, even the bride and groom. They don't know who these people are. Okay. When you try to have a conference in a city with 10,000 people, let's say something like SIGGRAPH, if you think of a really big conference, okay, you can't have this in many, many cities because there simply are not enough hotel rooms in most cities to accommodate 10,000 visitors. Okay. And the final thing, I guess, when it comes to complexity of scale, is that bad things will happen once you get a large enough N. So, if you have a football game where 100,000 people attend, one thing that is going to happen is that day, one of the people attending the football game or planning to attend the football game is almost certain to die. How do we know this? How long does an average person live? If an average person lives 100 years, how many days is that over a lifetime? If you're living to be 100 years, how many days is that? If I have that right, that's about 36,500 days. So 100,000 person days is the equivalent of 300 years of life. Okay. When you organize a big enough social gathering, okay, no, I once tried to organize the conference, and I got the specs from the organization, and they said that basically if your conference was going to be more than 20,000 people, like SIGGRAPH, make arrangements with a funeral home before the conference starts, so you know who to call if there's going to be a problem. Okay, there is going to be failure. Okay, and the same thing happens in distributed computation. If you have a world where you've got a lot of different computers talking to each other, if you're dividing a computation up between enough different computers, one of those computers is going to die during your computation, and you need to be able to arrange a system that will take care and deal with that. Next class, I'll talk about such a system, these MapReduce systems, things like Hadoop. One of the things that's very important about it is that it handles failure, okay? Because as N gets large enough, you're going to have such a failure. Any questions about that? Any questions about any of these issues of scale? Okay, if not, I will continue talking about this next class. I'll talk about Hadoop next class, but I want you, for now, I'm gonna say that's the end for today. And if you want to talk about projects, we can do it back at in the office hours, office hour meeting.